طيب وحضرت الامينو اسيدز مين شافها؟ كويس. كيف كان الكواليتي تبعت الساوند؟ واضح؟ بالمرة؟ بالمرة ليه؟ سيء 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 ما سيء مين بيقول واضح؟ معناته العلم بالكمبيوتر عندك كمبيوتر I heard it I thought it was fine. صح انه at one point انا كنت قاعد منعزل. صح انه زوجتي فكرت انه انا مش موجود في البيت فاجت شغلت التلفزيون عالي فطلع الصوت اذا طيب يس سير الكونديشن شغال بس قبل ما انتم تيجوا كان في 500 طالب قاعدين هون دول سنه رابعه اللي بياخذوا introductory كورس عقبالكم ان شاء الله فعشان هيك النفس تبعهم الاي تي بي تبعهم كان فعال ف that's why it needs some time معلش انا فطسان اكثر منكم يوم الخميس بعد الظهر كان كل بدهم ايانا للساعه 10 يعني there was sort of like مش negotiations لكن I had to be firm وحكيت لهم انا عندي محاضره الساعه 9 ليش؟ عشان يطلعوا بدري وتتحول شوي القاعه قبل ما احنا نجي. طيب انا I asked you to memorize the classification of amino acids, the abbreviations of these amino acids, and a little bit of the structure. And for example, I'm not going to give you or show you in the exam or whatever the structures of aspartate and glutamate and tell you what is this amino acid. You have no I'm not going to do that. The alanine, they belong to the same class. They are negatively charged. In the exam, I'm going to show you just one of them. I know حلو تعرفوا الستراكشر تبع هذا وهذا لأنه it will help you out later on. So they belong to the same class. يعني I just want you to know that this is a negatively charged amino acid. It could be this or that. فما راح أعطيكم بالoptions exam هو aspartate ولا glutamate. But I can give you something else يعني بالexam. I can give you all of the amino acids from other classes. These structures, you have to know what these structures are. You have to know what these amino acids are. For example, if I give you the structure of proline, for example, you have to know that this is proline. I don't want you to draw the structure of proline. But if you look at it, you should know what proline is, or that's what it is. ليش؟ لأنه كتير مهم تعرف الستراكشر تبع البروين to recognize the structure of proline. Really important لأنه له كتير effects على structure of proteins, other proteins. وهو هيك لحاله هيك يعني character هيك لحاله شخصيته اللي هو. Right? تفضل بس okay. let's review a few things عشان نكون on the same page قبل ما ندخل بهاي المحاضرة. What is the smallest amino acid? Glycine. يلا كلها بصوت واحد, okay? Glycine. What is the only amino acid that is achiral? Hello, glycine. What is the amino acid that has? What are the two amino acids that have sulfur in their R groups? Hello, histidine. Sorry. Methionine and cysteine. What is the name of the bond that characterizes cysteine? This disulfide. No, the R group of cysteine? No. Thiol group, SH. It's terminal, right? It's terminal. So it's important. Is it reactive? Is it reactive? Does it easily get into reactions? Yes. What is the name of the bond that two cysteines can form? Disulfide bond. Ash. What is the name of the molecule that methionine, the other one with sulfur group, can form? A derivative of methionine. It's small. S-adenosine methionine. هتبقوا تعرفوا. طيب. Mention the 3 amino acids that contain hydroxyl groups in their R groups. Serine, threonine, and tyrosine. Great. These hydroxyl groups of tyrosine, serine, and threonine can be modified in proteins. What's the name of this modification? Phosphorylation. Addition of phosphate groups. وهذا الphosphorylation مهم لأن هو اللي بيعمل regulation للproteins and protein structures. Great. What are the 3 amino acids that are aliphatic non-polar? Yep. And they are essential. Valine, leucine, and isoleucine. Remember, ايش هو the branching pattern of leucine and isoleucine? One of them at the beta carbon, اللي هو isoleucine, and the other at the gamma carbon, which is leucine. Right. And this is also important when we talk about protein structure. So this is the type of questions that I ask. There are 3 amino acids that are positively charged. What are they? Arginine, lysine, histidine. Histidine is the precursor of an important neurotransmitter and a signaling molecule. اللي هو ايش اسمه؟ Histamine. And histamine is important for allergy. Okay, فعشان هيك بتشوفوا you see these medications and they call them antihistamine. هذول against allergy. Okay. What is the amino acid that has a double ring structure? Tryptophan. What is the abbreviation of tryptophan? TRP. Tryptophan is the precursor of 2 important molecules we talked about. Melatonin and serotonin. Serotonin is a neurotransmitter. It's an important neurotransmitter. هذا اللي بيعطينا ايش؟ Feeling of happiness. Serotonin. And the other one is melatonin, which is important for skin pigmentation. So the more melatonin a person has, the darker the skin of that person. Yeah? Melanin, I'm sorry, melanin. طيب ايش كمان عندنا؟ What is the difference in structure between phenylalanine and tyrosine? Just a hydroxyl group. الاثنين فيهم الفينول group أو الفينول group. Sorry, phenyl group. التيروسين فيه الفينول group. Okay. And so on. Yani, this is the type of questions that I can answer in the exam. Right. Let's get into ionization of amino acids. So basically, the idea is what? The idea is that amino acids have two groups that can be ionized, which are the carboxyl group and the amino group. Right. Now, these two groups can be protonated and unprotonated. They can release a proton or they can gain a proton. And they can act as weak acids and bases. So the carboxyl group can actually function as a weak acid, while amino group can function as a weak base. So they have their own pKa's. All amino acids have that. So here, you have the carboxyl group and you have the amino group, and they can be protonated or unprotonated. And they have their own pKa values. What do I mean by that? Each one of them is different than the other. Meaning that at a certain point, the pKa of a carboxyl group is where you have 50% of the carboxyl group, not the amino acid, the carboxyl group. 50% of the carboxyl group is protonated, COOH, and 50% is unprotonated, COO minus. And the pKa of the amino group is the same thing. It's the pH, whereby you have 50% of the amino group protonated and 50% unprotonated. Okay. Now, there is this concept that is something known as isoelectric point. That's another term that you need to know. Isoelectric point is, that's the definition, it is the pH when, just like defining pKa, so isoelectric point, it's the pH where a molecule is ionized or charged, but the net charge of this molecule is 0. Meaning that the number of positive charges and negative charges is equal. So each one delete the other. Yes? So that's the isoelectric point. Now, the definition of pKa is, it is the pH when the concentration of the conjugate base is equal to the concentration of the acid, or the concentration of the acidic, the conjugate base form is equal to the concentration of the acidic form of this molecule. Yes? When a molecule reaches its isoelectric point, yani when a molecule reaches this pH, or when it exists in this pH whereby its net charge is equal to 0, we call this molecule, we say that this molecule exists in its Zwettrionic form. So a Zwettrion, it's a German word, a Zwettrion is the form of a molecule whereby it is charged, but the total net charge is equal to 0. Okay? So the idea here is that we have this amino acid right here at physiological pH. Physiological pH, that is a pH 7.4. The amino group is protonated and it's positively charged. And the carboxyl group is unprotonated, so it's negatively charged. Now the total net charge is, again, 0. So we said that this molecule, again, is in its Zwettrionic form. If we increase the pH, if we decrease the pH, that is, if we increase the concentrations of protons, what do? These two groups would be protonated. And if the carboxyl group is protonated, it becomes uncharged. If the amino group stays protonated, so it's charged, positively charged. The total net charge of this amino acid is +1. if we increase the pH, in other words, if we decrease the concentration of protons, what we do is that the groups would start to lose the protons that they bind to, that they associate with. So if the carboxyl group gets unprotonated, it loses its proton, it stays negatively charged. The amino group, if it gets unprotonated, it becomes neutral, meaning that the total net charge of this molecule is equal to -1. Yes? Negative. Okay. So let's say that an amino acid exists at very, very low pH. Very low pH. So in this case, the amino acid, the groups would be really happy and they would all have a proton associated with it. Because there is abundance of protons. So if the carboxyl group is protonated, it doesn't carry a charge at all. If the amino group is protonated, it carries a positive charge. The total net charge of this amino acid would be equal to +1. Sahih? No, this is protonated, positive charge, this is protonated, the charge is gone. If we increase the pH gradually, meaning that the concentration of protons would go down, the groups would start to lose the protons that they are associated with. The first group that loses the proton, its proton, is the carboxyl group. But the amino group would still be associated with that proton. So the amino acid becomes in this form, whereby the carboxyl group is negatively charged and the amino group is positively charged. Now, the total net charge of this amino acid, or of an amino acid in this form, is equal to 0. Okay? Increase the pH further, the amino group would start to lose its proton, meaning that it would be uncharged, and the total net charge of that protein is equal to, of that amino acid would be equal to -1. Now, the question is, when do these two groups, the amino groups and the carboxyl group, start to lose their protons? Well, it turns out that the pKa of the carboxyl group of amino acids is around 2. Meaning, so don't worry about the specifics. I'm not gonna tell you it's 2.34 like it's written in here. I'm gonna simplify it and tell you that it is 2. Okay? Now it's different for each amino acid, by the way. For some amino acid, it's like 2. For others, it's 1.8. For another group, it's like 2.3. For others, it's like 2.6. So it's different. So to simplify things, what I'm going to tell you that the pKa of the carboxyl group of amino acids is about 2. Now at pH 2, the 50% of the carboxyl group is in this form, in the protonated form, protonated uncharged, and 50% is in the unprotonated form, charged. So yes? Increase the pH further, all of the carboxyl groups are now in this form. All of them are unprotonated and all of them are uncharged. But the amino group stays protonated and charged. Now,
Doctor, you said that pKa is different between different amino acids. طب احنا ما عم نحكي عن الار جروب، احنا عم نحكي عن الستركشر which is common between all of them. ليش حيكون different؟ احنا بنحكي عن الكاربوكسيل جروب وعن
لأنه why? Okay, her question is, so why is the pKa different for the carboxyl groups of the different amino acids? Because of the R group. لأنه some R groups can attract electrons from the alpha carbon, meaning that these carbons would also be attracted towards carbon as well. يعني زي شيء بشد الثاني as well. So it's different. Okay. So now, increase the pH further. Now the protein, the amino acid is in this form, in this vitrionic form, which is what? This means that the amino acid is neutral. Even though it is charged, it's neutral because the number of negative charges and positive charges is equal. Yes? Now, increase the pH further. Now the amino group would start to lose its proton. The pKa is about 9. I'm not going to say it's 9.69 or 9.5 or 9.2 because it's different. For some amino acids it's 8.8. For other amino acids it's like 10. For the same purpose, same reason. Okay? Now, so at pH 9, the amino acid would be, half of it would be in this form, and the other half is in that form. Why? Because half of the amino acid would have this protonated positive charge, and half would be unprotonated, uncharged. So there are two pKa's for these two groups. For each amino acid has at least two pKa groups. One for the amino group and one for the carboxyl group. Right, yes? And remember, when the carboxyl group is protonated, it is not charged. If it is unprotonated, it is negatively charged. When the amino group is protonated, it's positively charged. When it is unprotonated, it's neutral. It's not charged. So they have the opposite rule, each one of them. Remember that. The pKa for this is 2, for the carboxyl group is 2, for the amino group is about 9. But yes? أي سؤال؟ Yes. مرة ثانية. Yeah, جيد. That's why I say that every amino acid has at least 2 pKa's. One for the amino group and the other for the carboxyl group. But each amino acid has a vitrionic form. So here is another look at it. That's pH. X-axis is pH. The y-axis is the fraction of each form. There are at least 3 forms. A form where there is all groups are protonated. That's when the pH is very low. All groups are protonated. When the carboxyl group is protonated, it's not charged. When the amino group is protonated, it's possibly charged. So it's very low at very, very low pH. The total net charge of this amino acid is +1. Increase the pH, the carboxyl group would start to lose its proton. So the fraction of this form decreases and the fraction of this form increases until we get to this point right here. What is this point? Where you have when the carboxyl group is half protonated and the other half is unprotonated. That's the pKa of the carboxyl group, which is around 2. Now, increase the pH further. You will have more of this amino acid converting to that. Eventually, you get to a point where all of the amino acid is in that form, is in the vitrionic form. That is, the total net charge is 0. See? Now increase the pH further. Now this, the amino group, will start to lose its proton, and it will be in that form. Okay, so the fraction of this vitrionic form decreases, the fraction of the other form increases. Until you get to this point right here, where you have 50% of the amino acid is in this vitrionic form and 50% is in that form. 50% is the total net charge is 0, and 50% the total net charge is -1. Okay? What is this point right here? What does it represent? What do do we call it? Yes? The pKa of the amino group, which is about 9. That's where you have 50% in this form, where this group is protonated, and 50% is unprotonated. Mashi? So that's the pKa right here. Right, yes? Can you follow that? Yes?
صار قيمة البيكا مش pH صح؟
ايه؟
قيمة
قيمة هذه قيمة ال pKa. Again, what is the definition of pKa? It is the pH. So it's a pH value. pKa is a pH value. So it is the pH when half of the amino acid or half of the amino group is protonated and the other half is unprotonated. ماشي؟ Conjugate base with acid, acidic form. كويس؟ Remember, we're connecting concepts to each other. So, أي سؤال فهمتوها ولا أعيد؟ أعيد؟ بعيد. نعيد من الأول. So the structure of amino acids is basically يا ابني اسكت يا حبيبي الله يرضى عليك اسكت. So this is the basic structure of amino acids. Where you have a central carbon, we call it the alpha carbon, and then you have the carboxyl group and you have the amino group. Now the carboxyl group and the amino group can be protonated and they can be unprotonated, meaning that they can release a proton and they can accept a proton. So they can act as weak acids and bases, just like buffers. So amino acids can function as buffers. Great. Since they can act, each group can act as weak acid or base, they have their own pKa as well. And pKa, the definition of pKa is, it is the pH where the molecule is half protonated, half unprotonated. The molecule is in its conjugate base form or in its acidic form. That's the definition of pKa. So basically, there is a pH value for amino acids where the total net charge of this amino acid would be equal to 0, even though it is charged. The number of positive charges is equal to the number of negative charges. We call this form of any molecule as baryonic form. Yes? And this pH, we call it, this pH value where a molecule is in its baryonic form, we call this pH value the isoelectric point. That is the point, the pH, whereby the molecule is charged, but its total net charge is equal to 0. Machine? So looking at an amino acid and how it looks like at different pH values is represented here in this plot. So basically, at very low pH, so the x-axis is the pH. At very low pH, there is abundance, there is a lot of protons in the solution. A lot. So all groups are happy. All groups are protonated. Meaning that the amino acid would look like this. All of it would be in this form. So when the carboxyl group is protonated, it doesn't carry a charge. But the amino group, when it's protonated, it will be possibly charged. The total net charge of this amino acid would be equal to +1. When you increase the pH gradually, what would happen is that the carboxyl group would start to lose its proton. Why? Because its pKa is low. What does that mean? It means that the association of the proton to the carboxyl group is weak. The carboxyl group starts to release this proton. The pKa value is 2, meaning what? Meaning that pKa is equal to, or the definition, it's the pH when half of the molecule is protonated and the other half is unprotonated. Half of the molecule is in the acidic form and the other half is in the conjugate base form. That's the pKa, which is about 2. So when you increase the pH to about 2, you'll notice that 50% of the molecule would have carboxyl group protonated and 50% the other half is unprotonated. This is the pKa value of the carboxyl group. Now increase the pH further. This form, this form would decrease in proportion and the other form increases. Great. This form, the one in the middle, is the zwitterionic form of the amino acid. Now, increase the pH further. Now, the amino group would start to lose its proton until it gets to this value right here, value that is 9, which is what? This is the pH when 50% of the amino group is protonated and 50% is unprotonated. 50% is positively charged and 50% is uncharged. Actually, this is the pKa. Eventually, once you increase the pH to a very high level, all of the amino groups of amino acids will be unprotonated, will be in that form. The total net charge of the amino acid will be equal to -1. منيح؟ Okay? So amino acids can function as buffers to weak acids and bases. So, except that it will have an amino acid like alanine with an R group of CH3, a methyl group. It has the amino group and it has a carboxyl group. This amino acid will exist in 3 forms. A form where all groups are protonated, so the carboxyl group is COOH and the amino group is NH3. A form where the groups are unprotonated, so the carboxyl group would be negatively charged and the amino group would be uncharged. Both of them are unprotonated. And a form where it is in the zwitterionic form, that is, the total net charge is equal to 0, whereby the carboxyl group is negatively charged and the amino group is positively charged. One is unprotonated and the other is protonated. Clear? So, such an amino acid would have 2 buffering capacities. So it can act as buffer. It can resist changes in pH. And there are 2 buffering capacities. One where the midpoint is the pKa of the carboxyl group, and the other is the pKa of the midpoint of the other one represents the pKa of the amino group. ماشي؟ Can you see that? في حد عنده مشكلة? Do you understand it? Okay. Notice the equivalence. Equivalence of hydroxyl groups, of the strong base that we're adding to that solution. So again, at very low pH, we have the amino acid in this form, and when you get to this point, to the midpoint, 50% is in this form and 50% is in that form. When you get to equivalence of 1, this means that the acidic group, the carboxyl group, is totally neutralized. It's all unprotonated. And you get to the midpoint of the amino group where you have 50% in this form and 50% in this zwitterionic form. Okay? And so on. Any questions? The question is now, what is the isoelectric point? That is, what is the pH value when an amino acid like alanine, for example, 100% of the amino acid is totally neutral. That is, number of charges, negative charges, positive charges is equal to 0. Yes? Sit, which is what? It's basically, it's actually 5.5. It's around 5.5, which is what? It's the average of the two pKa's. That is the pKa of the carboxyl group and the pKa of the amino group. At pH 6 or 5.5, so that is if we assume that it's 9 and 2. Okay. It's 11. Divided by 2, that's 5.5. So around pH of 5.5 or 6, if you will, this is where 100% of the amino acid is in this vitrionic form. So it's not arranged. It's not like you say, it's like from pH 5 to pH 6. No, it's a single point where 100% of the molecule is neutral. Okay? But any questions? So that's the isoelectric. Hello. What is the isoelectric point of glycine? خمسة ونص. ليش؟ Yes, خمسة ونص برضه. Why? Because it has only two groups that can be charged, that can be protonated, which are the carboxyl group and the amino group. pKa of the carboxyl group is 2, pKa of the amino group is 9, the average of both of them, that's 5.5. كويس? Same thing for many other amino acids. Valine, leucine, isoleucine, methionine, and so on. They all have almost the same isoelectric point, which is 5.5, because they only have two groups. Now for other amino acids, no, it's different. Which amino acids? The amino acids that have other groups that can be protonated or unprotonated, that can function as acids or bases. And there are a number of them. And these are, actually it's a longer list, but we'll focus on these. Arginine, aspartic acid, cysteine, glutamic acid, histidine, and lysine. These are really important amino acids. What's special about these amino acids? Look at it. How many do we have here? 6. How many amino acids are positively charged? 3. How many amino acids are negatively charged? 2. And we have an additional one, which is cysteine. ليش؟ لأنه it can lose its proton at a pH that is about 8. So these amino acids, these 6 of them, they can lose their protons, their R groups can lose their protons at pH that is near, well, not okay, that the body can utilize to steal their protons or to give them protons. The body can make them protonated or unprotonated. Okay? These are the 6 amino acids. Now there are others like threonine, serine, tyrosine. They can also be unprotonated, except that they can do so at pH values of about 13, really high pH values. But the R groups of these 6 amino acids, they can be protonated, unprotonated. The body can protonate these groups or unprotonate them physiologically. Okay? So you need to do what? You need to memorize the following. 1, the pKa of the carboxyl group of all amino acids is what? صحصح معي معلش شوية I think الجو صار أحسن بالقاع. It's about 2. The pKa of the amino group of all amino acids is 9. Now the pKa's of the R groups of these 6 amino acids you need to memorize them. So basically, for arginine it's about 12.5 for aspartic acid, and for glutamic acid it's 4. For cysteine it's 8, for histidine it's 6, for lysine it's about 11. Now you need to know what the isoelectric point of these groups are as well, of these amino acids, not the groups, of these amino acids are. Notice that they're different, they're not 5.5, they're different. They're like 3, 7.5, 10, 10.8, so you need to memorize these as well. And we will make 10.8, 11 to simplify things. So why is it that these isoelectric points are different? Let's look at one of them. أنا راح أسكت. Let's look at the ionization pattern of these amino acids. Let's look at glutamate. What is glutamate? It is a negatively charged amino acid. The R group of glutamate has a carboxyl group. It can be negatively charged. Its pKa, the R group of glutamate, the pKa of the R group of glutamate is about 4. So it has 3 pKa values. One for the carboxyl group, that is the alpha carboxyl group, the central carboxyl group of the amino acid, which is about 2. And then we have the amino group, and the pKa of the amino group is 9. And we have the pKa of the R group, which is 4. So there are 3 pKa values. So how about the isoelectric point? Well, let's look at it. Simply, what you can do is draw a titration curve, just like we did with buffers, because amino acids can act as buffers. So basically, again, look at the equivalence here. So here we have at very low pH, y-axis is the pH, at very, very low pH, all of the groups are protonated. The 2 carboxyl groups are protonated. The one that is central to that amino acid and the carboxyl group in the R group, both of them are protonated. And the amino group is protonated as well. And if the carboxyl groups are protonated, do they carry a charge? صحصح معاي. Do they carry a charge? No, they don't. If they are protonated, they are not charged. And the amino group, if it is protonated, would it be charged? Yes, it would. So the total net charge of glutamate at very low pH is +1. Great. Increase the pH slowly by adding more and more strong base. The pH goes up. You get to a point of about 2, whereby that's the pKa value of the carboxyl group right here. So at at pH of 2, you have 50% of this group protonated and 50% is unprotonated. Increase the pH further, it would all be in this form. Increase the pH further. Now, you remember that pKa of the R group is also 4. So it will start to lose its proton until you get to this pKa value, 4, which is what? This is the pKa, this is the pH where 50% of this group, of the R group, is protonated and 50% is unprotonated. صحيح? Increase the pH further and you amino group protonated and positively charged, and 50% unprotonated with no charges. Okay? It's acting like a buffer. There are 3 buffering capacities, 1 for each group. Question is, what is the zwitterionic form of glutamate? You have 4 forms, 1, A, B, C, D. What is the zwitterionic form of glutamate? It's B. This is the pH whereby the number of positive charges, which is +1, the number of negative charges, -1, are equal, and they're equal to the, so the total net charge is 0. This is the zwitterionic form. Question is, what is the isoelectric point? Exactly. It's 3. Why? We take the average of these 2 pKa values. Now, not the opposite, not the ones with the opposite charge. No. They have the same charge. But we take the average of these 2. So at pH 3, at this point right here, you have glutamate in this form, in the zwitterionic form. So the isoelectric point, or Pi, is about 3.
No difference.
That's what if you take the average of the pKa values of the same charge, of the 2 groups that have the same charge. This is, so for all the other amino acids except these 3, you take the average of the pKa values of the opposite charges. لأنه you need to keep in mind that what you're looking at is the form of the amino acid that is charged, but the total net charge is 0. Okay, so to understand it better, you need to draw a titration curve. So when you draw the titration curve and you look at these forms, you say, last way, I'm looking at the form where the amino acid is in the uncharged form, or the total net charge is 0. Sorry. So it's this form right here. So when do I have the amino acid in this form? Well, you take the average of pKa1 and the pKa of the R group. And the average is 2 plus 4 divided by 2, that's 3. So that's the isoelectric point of glutamate. Okay? So what is the isoelectric point of aspartate? Yes? Additional pKa تبعت الR group, it's 4. Aspartate, the pKa of the R group is 4. Isoelectric point is 3 as well. زي glutamate, just like glutamate. Why? Again, the best thing for you to do and really practice on this, draw a titration curve. That's the easiest way of you to understand it. So draw the titration curve. You have aspartate in this form at very low pH. Total net charge is +1. Increase the pH further. What happens is that this group starts to lose its proton. The negative charges appears at pH 2. 50% of this carboxyl group, I'm not talking about the amino acid, just talking about the group itself. 50% of the carboxyl group is protonated, uncharged, and 50% is unprotonated, negatively charged. Increase the pH further, now 100% of the amino acid would look like this. Increase the pH further. Now, the R group starts to lose its proton. Meaning that until you get to a point where you have 50% of the R group looking like this and 50% looking like that. That's the pKa value of what? Of this carboxyl group, of the R group. Okay? Increase the pH further, now the amino group starts to lose its proton. When it gets unprotonated, it loses its positive charge. Now, what is the total net charge of glutamate at very high pH? what is the total net charge of glutamate at very high pH? Minus 2. Okay? So it's looking like this. There are 3 buffering capacities again. 1 for the carboxyl group, the alpha carboxyl group, 1 for the R group, the carboxyl group of the R group, and 1 for the amino group of the alpha amino group. 3 buffering capacities. Now these 2 are equal to each other. Sorry, they're very close to each other. And the isolated point is the point in the middle. Okay? Yes? No, that's not like that. Okay. Questions? Yes? It's a definition of isoelectric point. It's the pH. When the molecule is charged, but the total net charges is equal to 0. So you have same number of positive charges and negative charges. At the isoelectric point. Okay? So if you look at glutamate, for example, if you look at an amino acid like alanine, if you look at an amino acid like alanine, there are 2 charged groups, the amino group and the carboxyl group. So when the pH is very low, the alanine, the groups of alanine will be protonated. When the carboxyl group is protonated, it doesn't carry a charge. When the amino group is protonated, it carries a positive charge. So this is not the Zwitterianic form. Okay? Now, when you increase the pH by increasing the concentration of a strong base, what happens is that now this carboxyl group would start to lose its proton. Now, the negative charge on this carboxyl group starts to appear, until you get to a point, so at pH of 2, 50% of the carboxyl group would be protonated looking like this, and 50% would be unprotonated looking like that. That's the pKa value of the carboxyl group. Now, increase the pH further, now all of the carboxyl groups would look like this, would be unprotonated, negatively charged. Now, the amino acid now has a positive charge and a negative charge. They cancel each other. So the amino acid we say is neutral. Okay? This is the Zwitterianic form. That is when a molecule is neutral. Total net charge is equal to 0. Increase the pH further, now this amino group would start to lose its proton, would appear like this. Eventually, at very high pH, the amino acid would look like this, where the amino group is unprotonated, uncharged, and the carboxyl group is unprotonated, negatively charged. The total net charge is minus 1. So this is the Zwitterianic form. This is where it appears at an isoelectric point. يعني ايش؟ يعني at a pH when this molecule is neutral. No charges whatsoever. So that's the amino acid. That's the isoelectric point of amino acid. Now if you look at the other ones that have R groups that can be ionized, well you have now 3 groups. Again, I'm راح أوقف. Now we have other amino acids that have R groups that can be ionized. So what happens in these amino acids is that they would have multiple charges, more than 2. An example is glutamate. At very low pH, all of the groups are protonated. The total net charge is +1 because these are protonated but they do not carry a charge. This is protonated but it has a positive charge. Now, this would start, the carboxyl group would start to lose its proton once you increase the pH. When you get to a pKa, 50% is in this form and 50% is in that form. 2, and 4. That is 3. This is where 100% of the amino acid is in this bit triangle. Again, increase the pH, you will have now the amino group losing its proton. The total net charge of this amino acid of glutamate is -2. Do the same at home for aspartate. That's the best thing for you to do. Let's look at histidine. Histidine is a very important amino acid because the pKa value of the R group is 6, which is near neutral pH. So it plays a very important role in our body. Now, these are the 4 forms of histidine. Now, in histidine, the amino group can be protonated charged. The carboxyl group can be protonated uncharged when it loses its proton. And the R group as well, it can be protonated or unprotonated. Now, at very low pH, the total net charge of histidine is +2 because this is positively charged and this is positively charged, but the charge on the carboxyl group is gone because it's protonated. Increase the pH, now the carboxyl group starts to lose its proton. The negative charge appears. But this stays protonated, positively charged. This stays protonated, positively charged. The total net charge of this molecule is +1 because you have -1, +1, +1 till these cancel each other, and eventually, so you have +1. Increase the pH further when you get it to pH of 6. That's the pKa of the R group. 50% of the R group is in this form, and 50% is in that form. That's the pKa of the R group. Eventually now, then when you increase the pH further, you will get 100% of histidine in this form, where the total net charge is 0. This is the zwitterionic form of histidine. Increase the pH further, now this becomes unprotonated, this is unprotonated as well, they are not charged, this is unprotonated, it's negatively charged, the total net charge is -1. Now, what is that's the pKa of 9, which is of this group right here. What is the isolated point? It's the average of these two. 6 plus 9 divided by 2, it's about 7.5. So at pH 7.5, 100% of the histidine is in this form. Now,